Good morning, class. Today is November the 18th. Yes. So this is the video for November 19th. And so we're continuing on electric power. And so today we're going to start by going over basically electrical generation. Or electric, let's call it electric generation. The changing magnetic field. And like all of electromagnetic theory, it started from observations. And so the observation was made that if you have a coil, all right, and you take a magnet and you move the magnet toward the coil, you will get a voltage. And I'm not going to label plus and minus right now. We'll get to that later, but basically a moving magnet causes you to get a voltage across this coil. And you know, it sort of is formalized because it was observed that moving the magnet required moving the magnetic field of the magnet in this direction perpendicular to the coil. Now, you know, sort of as we've gone through, I'm just going to write down Maxwell's third equation, and don't get too worried about it. I do it for completeness, and if you look at this equation, now first of all, you know, don't get hung up on the fact that it's a vector equation, and it's vector calculus and all that stuff. What it basically represents is that on this side you have a space derivative, a derivative with respect to like x, y, and z of the electric field. And on this side you have a time derivative of the magnetic field. And so what it's saying is kind of that the derivative of E with respect to space is related to the time rate of change of magnetic field. Now, this is, you know, you already know, related to something you already know, V is equal to L A guided T, the inductor law. Because, you know, this is basically voltage, and this is basically, you know, remember we found that the magnetic flux is related to L and I, and so these two equations you can actually derive one from the other if you work at it. Now, and so there's support for this equation already from the fact that we have observed that there is something called an inductor. And we're not going to, you know, in the notes I go through the entire mathematics. We're not going to do that today. It's not really necessary. But what I want to do is I want to point out a few things about this equation. This equation holds if there's no coil. All right, so the fact that I have a coil in this experiment is not needed. This equation will still hold even if the coil is not there. And what this equation means, if probably the chemical engineers in the audience, having gone through fluid mechanics and stuff like that, will be more in tune with what, you know, del cross E means. What del cross E means is that okay, means that E can form a loop. Now, that violates statics, right? Statics, we found that you have Q and Q minus, and the electric field, you know, does this, okay? And so for statics, what we found, or what we see, is that the electric field starts at a charge and it ends on a charge. So for dynamics, you know, now why am I saying dynamics? I mean, dV/dt is not zero. So if dV/dt is not zero, what this equation tells me is that E can loop in on itself. Now that's pretty dramatic because it violates a lot of things. What it means is that because, remember we've learned V is equal to the integral of E dot dl, that if I move along this circle, I will gain a voltage because E goes all the way around. And so it means that if I go from 1 to 1, I get a voltage that's not 0, which is you know, kind of weird. It's kind of like if you're climbing on a mountain and you went up the mountain, down the mountain, and you came back to the same place, you would have gained potential energy somehow. And so you know, that's what this equation means, and so it means that in space, if I have a magnetic field that's varying in time, and I go around a circle, I will gain a voltage, which is pretty dramatic. Now in the notes, what I say then is that if I take del cross E, if I take this equation and I perform the integral of E dot dl, and those of you that have taken some electromagnetic theory will recognize this as Stokes' law. The derivation is in the book, and so if this, you know, 4 del cross E is equal to minus B dt, that if you perform that integration around a loop, you will get negative the integral of the surface of B dot ds on dt. All right. So what is that saying? That's saying is that if I perform this integral E dot dl, and I have a magnetic field B, and I have to do dot products. Okay, so there's some, you know, vector stuff going on here, but don't worry about it. But basically, if I have a magnetic field that's a function of time, if I perform this integral for that loop, I will get a voltage V equal to this. And so we can rewrite that as the voltage for a loop is equal to, because I can interchange time and space derivatives like always, negative d dt, where phi is our flux, our magnetic flux like always, the integral of B dot ds. And so going from here, now, I realize that this may seem a little bit, kind of rushed and disjointed and everything. I'm doing this, more for the benefit that if you, see, I could have just written this down, okay, and I could have said, well, that's the immutable law of nature, that if I have a changing magnetic field, that if I go through some loop, it doesn't have to be a circle, that I will get a voltage when I come back to the same point that I was in the loop that's equal to the rate of change of the magnetic flux going through the loop. Okay, and I just wanted to connect you with, this is the more basic equation. It's related to this. And so, you can kind of think that this and the inductor law and this are all derivable from each other. They aren't derivable on their own. You can only start with one. We could have started with the inductor law, and I could derive this, and I could derive this. I could start with this, and I could derive these two. Okay, and so it just sort of, there's these three equations are interconnected with each other, and that's perhaps not helpful, but I mean, it just means you kind of have to start somewhere at some observation. All right, so now we can extend this, because now let's go to the coil. All right, well, the coil, if we assume that this coil is sort of tightly wound, all we do is we just add them up. It's just then just n dphi dt. And so and this is Lenz's law. And it was was the first observation really that he discovered that if I move this magnet at some rate of change that gives me a changing magnetic field through that coil, and I add more loops to the coil, I basically just multiply this by n to get the voltage that's developed across the coil. All right, so everyone always does the simple example then of a straight coil and a magnetic field. So I'm going to do my rough drawing here of a magnet. Okay, this is a magnet, a horseshoe magnet, north-south. And I'm going to put a coil in it. And I'm drawing this terribly. So my coil has two little terminals there for measuring the voltage, and I'm moving the coil with the velocity v, don't get confused with voltage, out of the magnet. And so in the notes in here, I'll redraw this on its side, so to speak. Here's the magnet, north, south. And so there's a magnetic field. Oops, I went the wrong way. All right, we're turning it on its side, and so basically, we're turning it this way. And so north is out of the board here, and so I have a magnetic field okay. So this corresponds to that face there of the magnet. And so my magnetic field is pointing into the board. And now what I do is I'm going to draw my coil. And my coil is moving with the velocity v. And now, this is the important thing to realize about Lenz's law is that it's based on the rate of change of the flux. The flux is this is equal to the B times the area the coil intersects with B. So the flux here, if this, I got too many x's here. Okay, well, sorry. Okay, if x is this dimension, then the flux is equal to the magnetic field, which is constant. And if this is h, is equal to B times this area, h times x. And in this equation, right, then the voltage is equal to negative dbhx dt. And so the b and the h are constant. Is equal to, and I'm going to get rid of the minus sign here because we're going to cover that in a little bit. bhv. So the voltage of the coil is equal to the magnetic field times this dimension times the velocity you're pulling it out of the magnet, v. Now, I haven't drawn a polarity here because you know, in principle you could use the minus sign here and this to figure it out, but there's so many, you know, minus signs going on here and flips of dimensions and things like that that I prefer to teach what the polarity is, thinking about the current that has to flow. Now, let me redraw my H over here. Now, if I put a resistor here, I didn't make enough room for a resistor. If I put a resistor here, then current is going to flow. Now, just logically, right, if I'm pulling this coil, then it should resist me pulling it, right? Because if I put a resistor there, I'm producing electric power, right? I'm dumping power in the resistor. And so pulling that coil should resist me pulling it. And so it means that there should be a force on the coil due to the magnetic field in the opposite direction. Now remember, this is equal to IL cross B. So in this case, it's IH cross B. But it's the cross product of I and B. B is pointing into the board, right? B. And so in order for the force to come in this direction, right, use your right-hand rule stuff, I cross B means I is in that direction. So that's how I want you to remember how to figure out what direction the polarity is, because by using your logic about what the force direction should be, it determines I is in this direction and the polarity is that way. So you know, what I'm basically saying is you can try and use Lenz's law on the minus sign and figure out what direction the voltage is, but it's sort of better to work from the fact that in some logical understanding of what direction the force, the magnetic force should be, because basically it has to resist me pulling it. Now, let's think about that magnetic force. Now we learned that power is equal to force times velocity. So the mechanical power now what is mechanical power? That's, I mean, somewhere there's an engine or there's me. But I'm supplying mechanical power to pull this thing to generate electrical power is equal to the force IHB, right? That's the force, times the velocity v. Okay, now electrical power is IV, right? The power I'm producing in my resistor. But we know the voltage, where'd it go, is BHV, so that's I BHV, and they're equal. All right, so what I've just shown is that for this simple electrical generator, that the mechanical power I have to supply to pull it through the magnet and generate a voltage and a current there is equal to the electrical power generated in that resistor. 100% efficient. Okay, and so unlike for the heat engine, which had an inherent fundamental physics thermodynamic limit of efficiency, of how much of the conversion efficiency between heat and work. The conversion from work to electricity theoretically can be 100%. Now it isn't because of various losses that occur, but that's why when we did that problem with the home generator, that I said just assume the generator part is 90% efficient, because it is typically very high efficiency, because there's an inherent 100% efficiency in the conversion. All right, so that's great. I'm going to go over here now and I'll erase this part. I'll leave that part there. Now, clearly, this linear generator is not very nice, because, I mean, once you pull it out, okay, you're done, right? And you can stick it back in, and so you could have some sort of engine that goes back in and out like that. But people realize very quickly that instead of doing that, what you want to do is, now let me draw my magnet again. So north, south. And what I'm going to do is I'm going to put a coil inside of that. If I can draw it. Okay, terrible drawing, sorry. But this is supposed to represent a coil inside that magnet that's turning along an axis. Okay, so I have some mechanism here where I can spin that coil inside there. And so let me redraw this. With my magnetic field B. Okay, here's magnetic field going from north to south, and I'm going to just draw this coil edge on here. And so basically, it is turning like that. So this is B. Now, so I'm drawing the coil as it is going in and out of the board, and then it's connected here somehow, and I'll go through that. So the flux then, if this is theta, and let's say this is L, and let's say this is H again going into and out of the board. Okay, the flux, now remember, flux is directional, right? There's this guy here. We haven't run into him yet, but here now we're running into him. We only care about the part of the magnetic field that's perpendicular to the coil. So the flux then is given by that part, and the flux is equal to B LH cosine, or sine theta. Right, because it's that dimension, right? It only counts this part, the part going through the coil. Now, if it's turning with a radial frequency omega, then theta we can write as omega t. Basically, it's spinning, and so we can write that the flux is BLH sine omega t. So now it's time varying for us. And then the voltage developed is goes as d phi dt, and so that's BHL omega cosine omega t. And don't worry about the minus signs again. If you want to figure out what the direction is, polarity is, go back and use force laws and things like that. So the voltage is going as cosine omega t, AC. Okay, now there's our AC power. Now I just want to, before I leave, this is called the dynamo. you'll see it's distinguished from another type of generator in a little bit. And I just want to walk through that, okay, for the dynamo, all right, if I draw V versus time, it's a cosine. All right, now think about it. All right, I define this such that at t equals 0, it's there, right? And so the maximum. Now what I'm going to do is I'm going to. So at the maximum voltage, it's on its side, and the flux is actually at a minimum. Okay? Because when the flux goes through a minimum, the rate of change of flux is actually at a maximum. So, you know, I want you to walk through this at home to make sure you understand the relationship between the voltage being developed versus time and the position of the coil. All right, because I probably will ask this on the quiz. All right, so just a little, you know, up front there. Now, at this point, the coil has rotated so that the flux is at a maximum, but the rate of change of flux is at a minimum. And it's kind of like, okay, you understand that from, you know, going back to first year calculus, that the maximum of flux, that's when the derivative is at a minimum. Okay, and then, and let me sort of mark this one so you see how it's rotating. And then at this point, it's continuing to rotate. Oops, other way around. Okay, so I sort of marked that one under the coil, and it's rotating. And now at this point, it's flipped the other way. That has gone over there. Okay, and it's continuing to rotate like this. And so the voltage versus time is related to the position of the coil by this pictorial here. Now, this is again called a dynamo, and it has one big problem. And the big problem is that, okay, if I try to draw in 3 dimensions again, which I'm very, very bad at, sorry. All right, this thing is rotating around an axis there. And it has these, you know, the electrodes coming off, you know, of V, but they're rotating too. And so if you try to like hook something up to there, it's kind of doesn't work. And so what people developed are what are called slip contacts on that, so that as it's rotating, you can pull V off of the slip contact. Now, obviously, that's kind of undesirable, all right, because, you know, I mean, you can imagine these slip contacts can wear mechanically, you can get arcing and all kinds of strange things. And so instead of making a dynamo, you make a moving magnet. Generator. And, you know, it's, you know, the same thing. I mean, because Lenz's law doesn't care, again, whether I move the coil or the magnet. It just, they have to move with respect to each other. And so what you do is you put your magnet on a rotating, you know, you're rotating it somehow. And you put a coil, you know, and you would arrange a coil on both ends because as it's going up here, it's increasing the flux, and so, you know, the voltage is one direction with respect to this, and so you have a pair of coils that you get a voltage off of them. And so this is what a real generator looks like. You rotate the magnet with respect to the coils. And so you see that every time the magnet comes up, it's producing a changing magnetic field in this coil, giving you a voltage, and this one's in the opposite direction. And so you get a single voltage from a coiled pair. in this generator. All right. Now that leads us into three-phase power. And so I'm going to go through a little bit of three-phase power because, all right, if you look at this, right, you can see something, which is that we're wasting a lot of space here. Because, I mean, it's like, okay, this magnet is moving through all this space here, and it's only generating voltage at this one point in the circle. So what you do is you take this moving magnet, north, south, rotating, and you have three coil pairs. So this one is V1, this one is V2, and this one is V3. And so this is, you know, this is, you know, basically using the space, because now when the magnet is rotating and it goes past this pair, it generates a voltage. When it goes past this pair, it generates a voltage. And it goes, and so you sort of fill in your space in the generator because you were wasting it before. Now, why three? So three phases. Why three? Well, I mean, I guess you know, it does turn out that you'll see sort of because of the relationships of sine and stuff like that. The three is kind of a special number here, mathematically. It's kind of a natural number to fill in the space, but you kind of just almost see that by the schematic. I mean, if you had four coil pairs, then you know you'd be piling them in. Two wouldn't kind of make sense because it's kind of like, well, then it seems like, you know, with just one there and one there, you are wasting a lot of space. So people do three, and so you get three voltages, V1, V2, and V3 coming out of this thing. Where V1 is equal to Vp1 sine omega t, Vp2. Now think about it. This is going to the next voltage is going to be out of phase. Now, if you think about it, okay, it's sort of hard to see, but if you know this is 1, this is 2, and this is 3, and now if I were to go to 4, I'd be back in the same place. So they're sort of evenly split in 360 degree space. So this is omega t plus 120 degrees out of phase, and this one is omega t plus 240 degrees out of phase. And you can also write that as 2 pi over 3, because 2 pi is 360. And you can write that as 4 pi over 3, because that's twice as much. All right, now, question is, okay, three-phase, what is it? All right, well, what it is, right, okay, think about it. You have V1, V2, and V3, and then you have a ground terminal. So if each one has a current, I1, I2, and I3, then it's just like three separate circuits, right? In fact, I could treat them as three separate circuits with respect to ground. So I have I1, V1 plus I2, V2 plus I3, V3. Oops. I3, V3. Now, that's in fact, you know, one way you can measure a three-phase circuit is just, you know, you measure each voltage down to ground. Okay, people tend to do it a different way, which is simpler. And if if I1 V1 is equal to I, well, let me write it differently. If I1, if all the currents are the same, and V1 is equal to V2 is equal to V3. That is, if you have, and many circuits, many three-phase circuits are arranged this way. You have essentially a balanced load on the phases. Then W, right, is just IV, and I'll write it this way, IP VP times sine squared omega t plus sine squared omega t plus 2 pi over 3 plus sine squared omega t plus 4 pi over 3. All right. Now, I mean, each one of these is just a sinusoid. So W average is just IP VP times, remember, that's 1/2, 1/2, 1/2, 3/2. All right. Now, remember, this is the peak. This is not the RMS yet. We haven't got there yet. This is the peak current, and this is the peak voltage. We'd like to write it in terms of RMS voltages. Now, so what I'm going to show here is that if I take V1 minus V2, now what am I doing here? Okay, instead of measuring each one to ground, I'm going to measure between two of the phases instead. Now, does it matter which one? No, okay, because they're all the same. I set that up in the problem. I said they're all the same. And so the fact that I'm writing 1 and 2, it could be 2 and 3 or 1 and 3, and you know, it doesn't matter. Just any two of the phases, I measure the voltage between them. If I do that, okay, that's V peak times sine omega t minus sine omega t plus 2 pi over 3. So this turns into a trig problem. Now, there's a trick to this, okay, and the trick is doing this. Okay, and I'm going to have to use brackets and stuff. Am I going to run out of room? I'm going to run out of room. Okay. Now, look what I'm going to do here. Omega t minus pi over 3 plus pi over 3 minus sine of omega t actually, I do it this way, plus and minus. Sorry, plus pi over 3 plus pi over 3. Okay, you see what I've done here? I wrote it such that they have a common variable, omega t plus pi over 3. And now you see we got our A minus B and our A plus B thing going. And you can look up the trig rules. And so I'm not going to write all, you know, the expansion of this. You can do this at home. You know, now that you know the trick, okay, writing it this way, and you treat that as your A and your B and the sign relationships, that you can put this all together, and it's VP root 3 cosine of pi, oops, of omega t plus pi over 3. Right. And so I have something else written here, but that has to be what it is. You just go through the expansion of psi A plus psi of A minus B and psi of A plus B, and you go through that expansion and you collect terms and stuff, and you come up with that as this. And so going back here now from this, I can write that VP, right, the peak voltage on one of the phases, is equal to V1 minus V2 over root 3. And so now I can rewrite this as 3/2 IP times V1 minus V2 over root 3. Yeah. And you see, you get a root 3 on the top. There's a 2 missing somewhere. Right, sorry, this is V over 2. Okay. And so if you then write, you can write that then as IP over root 2. Oh, sorry, there is no 2 involved. I did it right. I got it right to begin with. Yeah, no, that's right. And so I can write this, okay, so it's 3/2 V1 minus V2 over root 3 from that. So I can write that as IP over root 2 times V1 minus V2 over root 2, because root 2 times root 2 is 2, times root 3. So it's equal to root 3 I RMS V12 RMS. Okay, and that's very important to know because most circuits out there are in fact 3-phase. And it's sometimes you can't even access the ground wire. And it's so much easier to measure between the two of the phases. And if the phases are all the same, have the same voltage and the same current, then W3 phase average is given by I RMS, the RMS current in any of the phases, times the RMS voltage between two of the phases, because that's 1 over root 2, times root 3. Okay, so I wanted to go through and make sure you knew how to do that. Okay, good. And my time is okay. All right, and that's pretty much it. We walked through it. Now, I did want to, sort of for fun, go back to electric power. And talk about, okay, what happens now, if your house is here, okay, there's your house in some strange way. There's a pole down the street, right? That usually has 3 wires going to it, and there's this cylinder on the pole that's connected to 2 of them. And it's interesting if you ever think about this. Go down your street and look at the transformers going down the street, and you'll see that they switch off which of the 3 phases they take it from. But anyway, inside that transformer, there's coils, of course, and so and there's 3 wires then that go to your house. And so if you look at the transformer, it's called a split coil, and it's a step down, of course. I didn't draw it. Have both coils. It's a step down, of course, and so there's a whole bunch of coils on one side and then a few on the other side, because I want to step down my voltage. And what they do, so there's 3 wires, because I didn't draw it well, because you take what's called the center tap. And so going to your house, you have plus 120 volts and minus 120 volts, and then a setter tap, which is basically 0, is the idea. That'll be connected to ground in your house. And so in your house, if you go to your breaker box, which is this box that has a bunch of switches in it, okay, you might know of this box. You might know this box because, if you like hook up something to a circuit and you draw too much current, it might trip one of these breakers because, it's only rated to him. It's designed to do that so that you don't excessively load the system. Now, if you look at the inside of this box, you'll see that those 3 wires come into this box, plus 120 volts. Now, these are the RMS, by the way. Minus 120 volts and 0. And it's sort of interesting how this works. You have 2 bus bars going down, and they interleave with each other. So that to there, that to there. Okay, and then this goes off to a neutral bar, which is essentially ground. And so when you look at these breakers, they flip back and forth. They go between 120, plus 120 and minus 120, plus 120 and minus 120, etc. on each side. And because these go all the way across. And so most of the circuits in your house are just 120. And so if you look at it, there's a wire in here going off of one of them to somewhere, to a bunch of outlets in your house. But every once in a while, you see 2 of them gang together. All right, that's because plus 120 and minus 120 is going off to your house. So that's a 240 circuit. So for example, your oven would have wires from 2 adjacent breakers going off to your oven because it has to have a lot of power and supplying 240 volts. And as you know, power goes as V squared. We can write, okay, V is equal to IR, IV, and we can write it this way. We can write I as V over R, so V squared. So if I have 240 volts, I have 4 times the power. But anyway, I wanted you to be aware of that, and that's the final thing we were going to cover. So that if, for example, for Thanksgiving, I'm not asking you to do this. For Thanksgiving, you're going to use your kilowatt hour meters. I'm going to make that up soon. Try to think about that assignment of what to do. In principle, you could make measurements at your breaker box, and you'd have to understand that adjacent, that if I had 2 wires going into a breaker pair, that meant it was a 240 volt circuit. Okay, so I wanted to relay that. So you understand how to calculate 3-phase power. You understand electrical generation, and you also understand how the how home electric supply is arranged. Okay, that's it for today, and that's it until after Thanksgiving. All right, I'll talk to you tomorrow.